So let me actually back up to the list real quick, and I want to give you my secrets on how do you remember which of these names is for what, because they're all pretty similar to each other. Geologists sometimes go years in school struggling to keep it straight which one is which. A disconformity is when there's rock lost in time. Just like the disco. Nobody goes to the disco anymore. Disco has been lost in time. Disconformities are when there's just rock lost in time. That's the one where you can't see anything missing, but it's gone. Angular unconformities are pretty easy. The different layers are at angles to each other. Nonconformity is non-similar rocks touching each other. It's like your peas touching your carrots. And then the buttress unconformity is the last one. It's the more rare. It just has topography. Think of it as like a buried buttress around a castle. There's stuff there and it's all buried. So I said disconformities are the hardest to identify. There are some things that you can pick out sometimes that'll help, such as ancient river channels. The sediment in the bottom of a river is pretty distinctive. There's rocks and sand and silt in a certain way. And if it's cutting through other stuff and then filled in with that sediment, you know once upon a time that surface was the ground surface and that was a river. So that river was flowing through rock, exposed, time was passing, and it wasn't until later that sea level rose and the whole area gets flooded and deposits all over the place. So there was time missing at the point of that river channel. Also, if there's a basal conglomerate, so you have crystalline rock or even a sedimentary rock, continuous, nice, regular looking rock, and then you get to a layer that has chunks, pebbles, boulders of the lower level material mixed with material from the upper level. This indicates that there was erosion happening, breaking up the lower level, but then it suddenly started getting buried again before all those rocks finished eroding or washed away. Therefore, you know there was erosion going on, you know time passed. We can also do it with fossils. This may seem like the easiest, like, oh, hey, we have a Triceratops skull, and underneath is a plant fossil from way, way earlier, or in this case, a bone from the Jurassic period. Triceratops was Cretaceous, by the way. So Jurassic Park should have been called Cretaceous Park for anybody who's watched that movie. But here we have a Jurassic bone sitting directly on top of a layer containing a Cambrian fossil. There's a bunch of time periods between there. There's time missing. If you find rock that contains fossils, this is an easy way if you're good at identifying them. But most rock doesn't contain fossils, and not everybody's great at identifying every bone that they find in a rock immediately and knowing which time period it's from. Soil horizons. There is a difference between sediment and soil only forms due to organic interaction with sediment and breakdown and organic material adding in and water percolating through. It's a slow long-term process that happens at the surface. So anytime there's a soil horizon, which is distinctive to a geologist, you know that that was the ground. That meant there wasn't deposition, there was erosion, there was plant life and animal life maybe. There was stuff going on at the surface, time passing without deposition, then things get deposited on top. So what else happens to sediment? What other kind of structures are there? Well, compaction happens. You bury something under tons of rock, tons of sediment, it gets squished, it gets compacted. Not all of that sediment is equal strength, equal density. Stuff moves around when you compress it enough. It's called differential compaction. When, maybe a little to the left, there was denser stuff on top and the material is a little weaker underneath. On the right, a little less dense stuff piled on top and it's a little stronger. It's going to compact differently. So we can get structures called pinch swell structures. You can see here this layer running through the middle. In some places it's thicker, in some places it's thinner. By the way, trying to find a picture of this is not easy because pinch swell is not a Google safe term. Don't go trying to find your own pictures if you're at work on a work computer, for example. Another type of compaction structure happens due to diagenesis. This is a word that means changes after deposition. So the changes can be physical or chemical changes. And one of the prettiest, I think, is when we have pressure solution. The extreme pressure of the overlying sediment causes some of the grains to dissolve and not others along the greatest stress surface, which is not a nice straight line. It's this weird shaped line, and it results in stylolites. A lot of times this will happen in limestone that contains little bits of clay and other minerals. Some dissolve, some don't, and it results in these little super fine wavy black lines running through the limestone. A lot of times you'll see this in tile or countertops or bathroom walls or something like that because it's very decorative. It looks almost like somebody took a pen or a stylus and drew on it, but it's actually part of the rock. It's called stylolites. We can also get pitted pebbles. If you've ever taken a chunk of Play-Doh and pressed it against some marbles, for example, and then take the marbles off, you'll get a surface that looks, kind of like this rock on the left. The big difference is Play-Doh is really soft and squishy. Rock is not. So think about how much pressure it had to take to squish these divots into the rock. Tremendous pressure pressing pebbles against rocks and against other pebbles can result in surfaces like this. They're called pitted pebbles. Another extremely beautiful type of structure is called Lee-Seng-Gang banding. Lee-Seng-Gang banding is color banding in sandstone that doesn't run parallel to the beds. So it's not a red sandstone sitting on top of a yellow sandstone, which can happen, but rather it's red bands and yellow bands and white bands running in whatever angle and direction they happen to, cutting across the actual layers. And this happens, it's kind of like tie-dyeing a t-shirt. If you tie-dye a t-shirt, it doesn't change the orientation of the threads in the weave, but the color can go at any angle. And it happens when you have that dye in water and that wet dye goes through the cloth. When we have water that contains stuff, different salts and chemicals and minerals dissolved in it, running through rock, sandstone rock, or through sand that's still sediment and hasn't turned into rock yet, that water doesn't care where the beds are. It goes at whatever angle and flow that it wants, based on pressures and gravity and so forth. And it can leave stuff and stain the rock. There are another category of structures called pentacontemporaneous structures. These are things that happened almost at the same time as deposition. So it's still not tectonic stuff that happens long after, but it's not something that happened as the stuff was deposited. So it's not like that graded bedding that is a structure created by the deposition, for example. This is stuff that happened a while later. In a common human time frame, it could be something we would absolutely notice because it might be a year or two later, it might be 50 or 100 years later. In geologic time, that's virtually at the same time, but not quite, so we call it pentacontemporaneous instead of contemporary. For example, we can have a hill slope that's still soil and sediment, and it can slump. A big chunk of it just fall and slide down. That's a structure. It's a slump structure. It happened very soon after that sediment was deposited. The sediment never got a chance to be buried and lithified before the slump happened. But it could have been 10 years or even 300 years after it was deposited. It could be 10,000 years after it was deposited. Geologically, that's still soon after. Some kind of event usually causes this motion, this change to happen, such as a debris flow. It can result in those turbidites, but where it came from is now a structure like a canyon or a slump or something. It could be because of a storm or an earthquake or a stampede or something causing some shaking and weakening, or it could be a huge thunderstorm just soaking the area. Sometimes it'll slump as a whole, sometimes it'll create folds and wiggles, especially if there's an earthquake. And these kind of folds have very little symmetry and they're fluctuating in size and orientation relative to adjacent layers. For example, all these folds and wiggles here were caused by an earthquake, and the sand that was here was wet and it caused it to liquefy, called liquefaction. And then once the earthquake stopped, the stuff was all folded like this. Eventually it got buried and solidified into rock that maintained those shapes. The next thing to talk about for non-tectonic structures are salt structures. This is another case where it's hard to separate it from tectonics because without the plate tectonics, we couldn't have salt structures, but the salt structures themselves don't have to be caused by plate tectonics, so they're considered a non-tectonic structure. Now, salt is a sedimentary rock that forms from precipitation that happens due to water evaporating. It's like if you have water in a pan on the stove and you pour some salt into it, it all, dissolves in the water, so you have salt water in your pan, and then you boil all that water off. The salt precipitates out and leaves a white coating on the bottom of your pan. That's a salt deposit. That can happen naturally in a basin when you have water flow into the basin and then the water is evaporating and more water flows in and evaporates, and over time the salt can build up. We can get very thick accumulations in passive margin basins. This is a basin right near the edge of a continental edge. So it's near an ocean, lots of salt water. That basin can get water flowing into it, maybe not every year, but over, 1 million or 50 million years, salt water getting in there numerous times and evaporating numerous times can leave a lot of salt behind. Now, salt is weaker than other sedimentary rocks. If it's buried and pressurized enough, it can actually flow plastically. It's more like Play-Doh than like a rock, effectively, once you get enough pressure, especially pressure and heat. So how do we get these basins? Well, I mentioned the passive margin basins. It can also happen in a rift area. A rift basin where the continent is being ripped apart, it starts thinning and then tearing. We get a spreading center in the middle. It's lower and shallow, so it's not really an ocean yet by any means, even if we have water flowing in. It's more like a huge lake. But if it's connected in any way to an ocean, it's seawater that's flowing in. Even if it's not and it's just fresh water flowing in, even fresh water contains some salt. If you keep having water flow in and evaporate, and then more water flow in and more water evaporating, over time it concentrates that salt. Enough time and it concentrates the salt so much that it can't all stay dissolved, and it just builds up on the bottom. This can especially happen if we have sea level changes, which have happened thousands of times throughout geologic history. Either the land subsides, it sinks down, allowing water to flow in, or the sea level itself actually rises due to like melting ice caps and so forth, causing the seawater to flow in. But because the area is really shallow, the water can get much warmer. Think about on a sunny day, which is warmer, a puddle on the shore or the lake water itself. The puddle gets much warmer. It's shallow, doesn't take much energy, the sun can warm the whole thing. So when we have shallow water, it gets warmer, more evaporation takes place. We can, over long geologic periods of time, get very thick layers of salt, hundreds of feet thick. Halokinesis does not mean bad breath. Halokinesis is movement, kinetics, movement of salt. The halo, like halite. We can get movement because of density inversion. This is kind of like those little globs of sand sinking down into the mud, just on a much more extreme scale. You can have sandstone and shale and limestone and all these denser rocks sitting on top of a sand layer or a salt layer. That salt layer gets more and more pressurized the more sediment is above it, and it'll start flowing plastically. Positive buoyancy force is when lower density material tries to rise above the high density stuff. So those high density rocks sitting on top of the salt try to sink, and the more buoyant, less dense salt tries to rise. Again, think of the lava lamp. Differential loading, just like we had with the pinch swell structures on a small scale. Now think on a bigger, broader scale. It's like, you've got that Play-Doh sitting on your desk. You press down on one side, it squishes out on the other side where there's less pressure. It's just air pressure on that side. On the side you're pushing on, there's all that pressure from your hand. Salt will move like that from the high compression area to the lower compression area. Sometimes it can result in domes. This is a salt dome that's been mined, so there's not a lot of salt left. You can see the underside of the layers that were on top of the salt. That's what the salt pressed itself up into. Basically somewhere all around was higher pressure and squished the salt into this dome. Now we're mining it and taking it away, leaving a really beautiful cave, by the way. So salt domes aren't the only shape it can result in. Your textbook has a bunch of drawings and diagrams that show different salt structures. Some things that can happen are a source bed thins and disappears so that the salt is now above a younger layer, and in contact with it, this type of contact is a primary weld. It's basically, it touches it and then solidifies like that, and so now it's welded together. We can have upbuilding, which describes when salt moves upward in relation to where it was originally. Downbuilding is when it moves downward because of the way it's squished. That's where there are cracks and weaknesses for it to flow into. Table 2.5 on page 28 in your textbook has more terms. These are, some of the key basic ones.